Take a sip of water, right now, and think about where it actually came from. Not from a cloud, not from a river, not even from the ice of some ancient glacier. Some of the water molecules in that sip are older than the sun itself. They formed as ice, on the surface of frozen dust grains, in a cloud of gas drifting through interstellar space. That cloud existed before our solar system did, before the sun had ignited into a star at all. Scientists can prove this using a simple ratio hidden inside every water molecule. It's called the deuterium-to-hydrogen ratio, and it works like a fingerprint stamped onto water wherever it forms. Different environments in space leave different fingerprints, and Earth's oceans carry a very specific one. That fingerprint has been traced back, molecule by molecule, to the cold heart of a molecular cloud. Some estimates suggest up to half of Earth's water predates the sun's birth by millions of years. You are drinking, digesting, and made of matter that watched our star being born. By the end of this video, you'll understand exactly how water this old ended up inside your body. To understand this claim, you need to understand one specific atomic ratio. Ordinary hydrogen has one proton and no neutrons in its nucleus. Deuterium is a heavier version of hydrogen, with one proton and one neutron instead. Chemically, deuterium behaves almost identically to hydrogen. It still bonds with oxygen to form water. But water made with deuterium, sometimes called heavy water, carries a distinct atomic signature. Astronomers measure the ratio of deuterium to ordinary hydrogen in water, known as the DH ratio. That ratio isn't the same everywhere in the universe. It depends heavily on temperature and formation history. In warmer environments, deuterium tends to get diluted out. In extremely cold environments, it becomes enriched. This means the DH ratio works like a kind of cosmic thermometer and location tag combined into one number. If you measure the DH ratio of a sample of water, you can make an educated guess about where and how cold it was born. Earth's oceans have their own well-measured DH ratio, a baseline scientists call standard mean ocean water. Every other water sample in the solar system gets compared against that baseline. Comets, asteroids, meteorites, even the atmospheres of other planets, all carry their own distinct ratio. To trace water's origin, you first have to go to where most of it was actually made: interstellar molecular clouds. These clouds are vast regions of gas and dust, scattered across a galaxy, often many light years across. Inside them, temperatures drop to around 10 degrees above absolute zero. At that temperature, tiny dust grains, each barely a fraction of a millimeter wide, become extremely efficient chemical factories. Hydrogen and oxygen atoms drift through the cloud and stick to the frozen surface of these grains. Once stuck, they can slowly migrate across the grain's surface and react with each other. Hydrogen atoms bond with oxygen atoms directly on the ice, building water molecule by molecule. This isn't happening in a lab or on a planet. It's happening on grains of cosmic dust, drifting in near total darkness. Over hundreds of thousands of years, this slow process coats dust grains in a thin shell of water ice. It happens continuously, throughout the galaxy, in nearly every cloud cold and dense enough to allow it. Our own sun was born inside exactly this kind of cloud, roughly 4.6 billion years ago. Before the sun existed as a star, the raw material for its future planets was already coated in ice. That ice included water that had never touched a planet, a comet, or a drop of liquid rain. This isn't just theoretical chemistry. Astronomers have directly observed it happening. Dutch astronomer Ewine van Dishoeck at Leiden Observatory has spent decades studying water in star-forming regions. Using infrared telescopes like Herschel and Spitzer, her team detected water vapor and water ice in clouds actively forming new stars. Herschel's dedicated water-observing program, called WISH, tracked water molecules across dozens of these stellar nurseries. The data confirmed that water ice is not rare in these clouds. It is abundant, almost everywhere astronomers looked. Some of the water detected in these regions was forming in real time, in clouds that hadn't yet collapsed into stars. In other words, telescopes have watched water molecules assemble in the exact kind of environment our solar system was born from. This turned an elegant theory into an observed, ongoing, galaxy-wide process. Water, it turns out, is one of the most common molecules in the universe, and one of the earliest to form. Once a molecular cloud starts collapsing under its own gravity, it flattens into a spinning disk of gas and dust. This is called a protoplanetary disk, and it's the raw construction material for an entire future solar system. At the center, matter piles up and ignites into a new star. Around it, the leftover material keeps spinning. This disk isn't the same temperature everywhere. Close to the new star, it's scorching hot. Farther out, it's cold enough for water to freeze solid, rather than exist as vapor. Astronomers call that boundary the snow line, or the frost line. In our own solar system's early disk, the snow line sat roughly where the asteroid belt exists today. Beyond that line, icy planetesimals, small building blocks of future planets and moons, could form and grow. Inside that line, it was too hot for ice to survive, which is part of why the inner planets are dry, rocky worlds. Earth formed well inside that snow line, in the hot, dry portion of the young solar system. By simple geography, Earth should have formed almost entirely without water, which raises an obvious question. If Earth formed too hot for water, where did our oceans actually come from? For decades, the leading suspect was comets, icy leftovers from the outer solar system that occasionally streak past Earth. Comets seemed like an obvious answer. They are, quite literally, balls of ancient ice. In the 1980s and 1990s, astronomers measured the D-H ratio in several comets, including Halley, Hyakutake, and Hale-Bopp. All three showed a D-H ratio roughly twice as high as Earth's ocean water. That was already a warning sign, but comets are not all identical, so the search continued. In 2014, the European Space Agency's Rosetta spacecraft arrived at Comet 67P, formerly named 67P Churyumov-Gerasimenko. Rosetta carried an instrument called Rosina, designed specifically to measure the isotopic makeup of the comet's water vapor. In 2015, physicist Catherine Altwegg and her team published the results in the journal Science. Comet 67P's water carried a D-H ratio roughly 3 times higher than Earth's oceans. That result made this particular class of comet a poor match for Earth's actual water. If comets like 67P and Halley were the main source, Earth's oceans should carry their heavier isotopic signature. They don't. Attention shifted toward a different class of object entirely, carbonaceous chondrite meteorites. These are primitive, water-rich chunks of ancient asteroids, some of the most unaltered material left over from the solar system's formation. In 2012, planetary scientist Connell Alexander and colleagues published an extensive analysis of these meteorites in the journal Science. Their D-H ratio matched Earth's ocean water far more closely than any comet measured so far. The evidence increasingly pointed toward asteroids, not comets, as the dominant source of Earth's water. It was a case of cosmic mistaken identity, corrected only by precise isotopic detective work. The suspect looked right. The chemistry said otherwise. Water's true delivery vehicle turned out to be dry-looking rock, not glittering ice. But asteroids alone don't explain how water-rich material reached Earth's orbit in the first place. Earth formed in a region of the disk that should have been relatively dry and asteroid-poor. In 2011, a team of planetary scientists proposed a solution called the Grand Tack hypothesis, published in the journal Nature. The lead author, Kevin Walsh, argued that the young planet Jupiter didn't stay in one place. Jupiter initially migrated inward, toward the Sun, before reversing course and migrating back outward. As it moved, Jupiter's gravity scattered huge numbers of water-rich asteroids out of their original orbits. Many of those asteroids were flung inward, directly into the region where Earth was still forming. Some of that scattered material was captured by Earth's gravity, arriving as meteorite impacts over hundreds of millions of years. Jupiter, in this model, acted less like a bystander and more like a cosmic delivery service. Without that early gravitational shuffling, Earth may never have accumulated enough water to form a single ocean. Here is where the story becomes even stranger. Some scientists asked a deeper question. Did the water that formed as interstellar ice get destroyed and remade during all of this violent history? Forming a star, a disk, and a planet involves enormous heat, radiation, and repeated collisions. In 2014, astrochemist Ilsa Cleeves and colleagues at the University of Michigan modeled exactly that question in a paper published in Science. They calculated how much cosmic ray radiation would be needed to fully reset water's D-H ratio during disk formation. Their models showed that typical protoplanetary disks don't generate nearly enough radiation to erase the original interstellar signature. Their conclusion was striking. A significant fraction of the solar system's water was never actually remade at all. It survived, as ice, drifting through the collapse of the cloud, the spin of the disk, and the formation of planets. By their estimate, as much as half of Earth's water may be inherited directly from that pre-solar interstellar cloud, not reprocessed, not remade in the heat of the young solar system, simply carried forward, molecule by molecule. Some of the water in your body, by that estimate, is literally older than the sun that lights your sky. Comets, asteroids, interstellar ice modeling, and isotopic fingerprinting all independently point toward the same conclusion. Earth's water is not simply old. Much of it never really had a birthday at all, at least not one that coincides with our planet's. Think about the glass of water sitting near you right now, or the last sip you took. Some of the molecules inside it followed an almost unbelievable journey to reach your lips. They began as scattered atoms, drifting through a dark, frozen molecular cloud, long before any star existed nearby. They froze onto microscopic grains of dust, one atom at a time, over hundreds of thousands of years. That dust, and its icy coating, became part of the cloud that collapsed to form our sun. Some of it survived the birth of that star completely intact, according to Cleeves and her colleagues. It drifted through the swirling protoplanetary disk, past a chaotic, migrating Jupiter. It was flung inward, riding on the surface of an ancient, water-rich asteroid. It fell to Earth as a meteorite impact, sometime in the planet's first several hundred million years. It became part of an ocean, then a cloud, then rain, then a river, then a reservoir. Eventually, through some combination of agriculture, plumbing, and pure chance, it reached a glass, and then reached you. None of that journey required your permission, your awareness, or your existence. It happened billions of years before you, or anyone you have ever loved, was born. And yet it ends, for this brief instant, inside you, being read by neurons made partly of the same ancient material. This is not a metaphor for connection to the cosmos. It is a literal, traceable, chemical fact. The oxygen and hydrogen atoms in your body were forged and assembled before Earth existed as a planet. Some of them are older than the ground you're standing on. Some are older than the sun overhead. You are not simply living on a very old planet. You are built, in part, from material that predates the very fire that keeps that planet warm. That is not a small thing to be true about a sip of water. Every time you drink, you are, in a small and literal way, tasting the early universe. The same molecules that drifted, frozen, through interstellar dark, are now warm, moving, and alive inside you. Nothing about that history required consciousness, or meaning, or intention. And yet here you are, made of it, aware of it, for exactly long enough to notice.